Welcome to today's Explainer. We are going to look at a genuinely fascinating new research paper today, one that actually completely shatters a long-held belief in the AI community. For years, the accepted wisdom has been that AI language generation absolutely must be done sequentially, reading and writing from left to right. But what if that's entirely wrong? What if a model could just look at the whole picture all at once? Today, we're unpacking the story of a brand new model called ILLaDA, which proves exactly that. Okay, let's dive into this. Here is our roadmap for today. We'll start with the autoregressive monopoly, enter the diffusion challenger, look at building a better brain, get into the benchmark showdown, and finally, wrap up with the future of diffusion. You can really think of this as a true David versus Goliath story in the rapidly evolving AI landscape. Section 1. The autoregressive monopoly. Right now, household names in AI, like GPT and QN, absolutely dominate the market using what's called the autoregressive paradigm. That means they generate text sequentially, strictly left to right. Bidirectional diffusion, on the other hand, tackles generation in a completely different way. Think of it like a giant jigsaw puzzle. Instead of building it piece by piece from one corner, you're filling in pieces from the edges, the middle, and all sides simultaneously until the full picture emerges. The researchers state their mission here so perfectly. They are, quote, challenging the common belief that language intelligence must rely on autoregressive modeling, end quote. This paper isn't just about dropping another new model into the market. It's about breaking a fundamental assumption in AI development. They're testing whether that left-to-right monopoly is actually the only path to high-level language intelligence. Section 2. Enter the diffusion challenger. Let's meet ILLaDA. So how does this challenger actually work? Well, it relies on masked diffusion. Basically, during training, researchers hide or mask random words in a sequence, and the model uses fully bidirectional attention to predict all of those missing words simultaneously. It analyzes the entire context all at once. It's looking forward, it's looking backward, and everywhere in between, which is totally unlike traditional models that only ever look backward. Now, as a proof of concept, the original ILLaDA was a bold first attempt, for sure. It proved that a diffusion model could actually acquire core capabilities, like following instructions. But honestly, it remained heavily outmatched by dominant autoregressive models like QN 2.5. It was a promising underdog, but it just wasn't quite ready for the heavyweight title yet. It needed to get stronger. Section 3. Building a better brain. This is the training montage phase, where researchers massively scale and engineer our underdog into a true, polished contender, ILLaDA. To build a better brain, you need massive scale. I mean, the original model was trained on just over 2 trillion tokens. But for ILLaDA, they ramped that pre-training corpus up to a staggering 12 trillion tokens. This gave the model a vastly richer and broader understanding of the world. But of course, data alone isn't enough. The architecture itself needed a major upgrade. And those architectural upgrades were absolutely crucial. They implemented grouped query attention to slash inference memory. They tied the input and output embeddings together, keeping the parameter count super lean at 7.6 billion. Plus, they introduced variable links generation for much faster block-by-block text output, and added a brand new confidence-based scoring rule for multiple choice evaluations. Put that all together, and you get a model that is leaner, faster, and significantly smarter. Now, what's really interesting about this is what happens next. After pre-training on those 12 trillion tokens, ILLaDA undergoes supervised fine-tuning, or SFT, on a 25 billion token instruction dataset. When tracking performance on the GSM-8K math benchmark, the model was trained for 12 full epochs. That means it went over the exact same data 12 times. The longer it grinds, the smarter it gets. And we see that same continuous upward trajectory on the even more difficult math benchmark. The researchers highlight a genuinely fascinating trait here. Diffusion models act as super data learners. Unlike some traditional models that might plateau or just overfit quickly when looking at the same data repeatedly, ILLaDA uniquely benefits from this repeated training, literally squeezing every drop of reasoning capability out of the data set. Section 4. The benchmark showdown. All right, it is time to see if our newly upgraded underdog can actually step into the ring and compete with Goliath. Let's look at the base models before any instruction tuning. ILLaDA's improvements are massive across the board compared to its predecessor. But the real story is how it stacks up against the autoregressive heavyweight QN 2.5. On major reasoning and knowledge benchmarks, we're talking MMLU, BBH, RCC, and GSM-8K, ILLaDA isn't just surviving, it is actually outperforming Qwen 2.57b. A diffusion model is beating a top-tier autoregressive model. So the crucial point here is the sheer scale of the leap from the previous generation. Just by making those architectural tweaks and scaling up the data, ILLaDA jumped an astonishing 21.6 points on the BBH benchmark, compared to the original Lambda model. That is a night and day difference in reasoning capability. However, to be completely impartial, when we look at the instruct models, the ones fine-tuned to follow complex chat prompts, the story shifts just a bit. While ILLaDA closes the gap rapidly, jumping 14.5 points on math and 16.5 points on the human eval coding benchmark, the autoregressive Qwen 2.5 instruct model definitely still holds a clear edge in advanced code and mathematical generation. Section 5, the future of diffusion. Let's move to and see how this builds, because why exactly does that performance gap exist in the instruct models, and what comes next? Well, the researchers point out a very specific reason for that remaining gap, and it actually isn't a failure of the diffusion architecture itself. Rather, ILLaDA simply hasn't yet undergone reinforcement learning alignment. Qwen 8.5 and really all top-tier autoregressive models use intensive reinforcement learning as a final polish to perfectly align the model's outputs with human expectations. ILLaDA, it just stopped after supervised fine-tuning. So the immediate next steps for the researchers are pretty clear. They need to implement reinforcement learning methods tailored specifically for diffusion models, things like VRPO or diffuGRPO. Beyond that, they plan to scale the model well past 8 billion parameters and really push the limits of this fascinating phenomenon, where diffusion models act as super data learners under repeated pre-training. The ceiling for bidirectional diffusion models? It's still completely unknown. Which leaves us with this final thought. We've just watched an underdog architecture scale up and suddenly go toe-to-toe with the heavily optimized left-to-right models that have completely monopolized AI for years. If a diffusion model trained from scratch can catch up this fast, will left-to-right generations soon be a thing of the past? It is a thrilling question for the future of AI. Thank you so much for joining me to unpack this amazing source material in today's explainer. And keep exploring.